Now let's talk about Cherenkev counter. It's a detector, and it detects the particles uh, by by virtue of their trajectories, by virtue of their interactions. Now, this if I suppose that we have a medium, and when we hit this medium with fast electrons, suppose we have electrons, fast electrons. I mean here beta particles. Now, what happens is that when fast moving charged particles, when they pass through this transparent uh, medium, what it does is it produces some special kind of visible light. And this visible radiation happens to be possible if the velocity of the particle is greater than that of light in this material medium that we are talking about. Now, if the velocity of the particle, the charged particle that we have, uh, if its velocity is greater than that of velocity of light in this transparent material medium, then certainly what we have is we have the visible radiations. And this effect was basically discovered by Cherenkov, and the radiations that are associated with this process are called as Cherenkov radiations. Now, if I assume that a beam of particles, which I chose as beta particles, is incident normally on a thin sheet, and let me take a thin sheet like this, and and what am I trying to do is that I'll call it AB, and what am I trying to do is that I assume that the beta particles are incident on this thin sheet of transparent medium. Now, this thin sheet may be a crystalline solid, and we understand what a crystalline means. A crystalline substance is a substance where we have long range of order between atoms or molecules in a solid. Now, so we can think of using a crystalline material. Uh, Now, what happens is that on encountering the molecules inside this medium, the electrons will suffer the changes. They will suffer the changes of velocities, and which are small compared to the velocity of the beam. So there will be changes inside the material. Now, as the charged particles experience a succession, so you will have successive collisions, we will have small accelerations that will develop inside the material. And what it does is it emits electromagnetic radiations, which lie in a visible region uh, and have a continuous spectrum. Now, the radiations leave in all directions from this transparent material. They will leave in all directions. But they happen to have certain directions, some preferable directions, where the effect is enhanced, and this effect is enhanced by virtue of constructive interference between the neighboring beams that are present in the material. So when we say constructive interference, that means the resultant amplitude is going to be more. You have the superposition of the waves. So if I assume that, if I suppose the mean velocity of these particles over a small distance, CD, I'll choose a length CD here, and and the velocity over this small distance is v, right? And the velocity of light in the medium is simply it will be C by mu. So if I choose mu as a refractive index, if I choose it as a refractive index, then what will be the velocity of light in this medium? The velocity of light will be C by mu. And that should be clear. And we understand that this c is the speed of light in vacuum, and we have this mu. Mu is the refractive index of the medium that we have chosen, and it has a dependence on the wavelength of the light. Now, if I assume a parallel light paths, in this case, if I assume some parallel light path, so let me have a geometrical way of doing it. So if I assume a parallel path from C and a parallel path from D. Okay, so this is not to be the edge. That should be kept in mind. Okay, so let me assume this is X and this is Y. And certainly you have the path difference here. So we can see here that we have taken two parallel light paths like Cx and dy, which make an angle theta with a beam of beta particles. So this angle is theta. Okay, so what we try to do is we are trying to calculate some kind of path difference. So what will be the path difference between Cx and dy? This Cx and dy, if I name this point as E. So path difference between Cx and dy, and that's going to be simply CE. So this CE will be the path difference. Now, if the time taken by the light to travel from this point C to the point E that we have is equal to the time taken by the electron to travel from C to D, then the points that we have D and E, they should be in the same phase. And the two rays that we have chosen here, they should reinforce each other. And hence, we have the condition of reinforcement. We have a condition of reinforcement. Now, what is that? That is, I should write here, condition of reinforcement. Now, what is that? That is the CE. Okay, divide by the velocity of light in material medium. What's that? That is C by mu must be equal to CD divided by velocity with which the electron is moving. This should be the case. So we can look at it in a pure geometrical way, and what we will have is we can have CE by CD. That will be C by mu V. Okay, so I bring this CD down and take this C by mu up. So what we will have is that the ratio between this CE by CD will be C by mu nu. That should be the clear case. Now this relation that we have, this relation is called as Cherenkev relation. We call it Cherenkev relation. And the Cherenkev radiation is not confined to one plane. It's not confined to the single plane that we are talking about. But it is propagating along the surfaces of the cones that we can imagine here. And there is what we have is the coincidence. We have the coincidence of the waves, of the light waves and the and electron. So, so this is our Cherenkov relation, and we can think of this triangle that we have. It's something like this and this and this, and this is 90. This is theta. Now this is C, and this is D, and this is E. Now this CE by CD is simply cos theta. So cos theta is CE by CD. So what does that mean? That means cos theta is equal to C by mu nu. I can write like this. There's nothing wrong with it. And this cos theta, what is the maximum value of cos theta? Maximum value of cos theta is simply 1. So if I take the maximum value, then I'll have C by mu. This is not nu, please, this is V. This is the velocity of the electron. Velocity of the electron. Velocity of the electron. So what does that mean? This velocity of the electron is simply C by mu. That should be the case, right? And we will have this V is giving us the velocity of the electron. Okay, so what we have here is V is equal to C by mu. Now we can also look for, now this C by mu that we have, we call this C by mu as, we call it C by mu is called, it's called a threshold velocity. Threshold velocity. And we can also calculate the maximum value of theta. We can calculate the maximum value of theta. Now for maximum value of theta, what should be the case? For maximum value of theta, this what we call as V, the velocity of the electron should be equal to the velocity of the light in vacuum. So in that case, that's possible only when V is equal to C. So in that case, the cos theta that we have is, which is basically C by mu V. Now, if V is equal to C, then cos theta is gonna be 1 by mu. And theta, now this theta is maximum theta. This maximum theta is gonna be cos inverse of 1 by mu. Now let's take an example let's take an example of a material which is commonly known as lucite, and this is considered as a Cherenkov detector. And we are not interested to go into the details of this material. What is important here is that it has a refractive index of 1.5. And for electrons, for beta particles, which are energetic enough to have an appreciable range of range in this lucite, and produce Cherenkov radiations. So for that, what we need is, we want to calculate the threshold velocity. The threshold velocity. So what will be that? That V is C by mu, and C is 3 times 10 to the power of 8 meter per second, divided by 1.5, 1s are, 2s are. So V is going to be 2 times 10 to the power of 8 meter per second. This is going to be the threshold velocity of the electrons that will be used to produce Cherenkov radiations. And at the same time, we can calculate the maximum angle. So what is the maximum angle. So for that, what we have cos theta, this theta is max, that is equal to 1 by mu, and that is 1 by 1.5, and that is nearly 0.667. And for this, the corresponding value of theta can be found is 48 degree approximately. So what we calculated here, what we got here is theta max and the velocity and the threshold velocity. Now, if we suppose that all the Cherenkov radiations emitted in this case, they lie in visible range. They lie in visible range, and a fast electron in lucite produces about, say, for example, 500 photons per centimeter of its length. Now, to move on from here, if we want to calculate the kinetic energy of the fast-moving particles under the relativistic conditions, what should we do here is that the kinetic energy that we have under relativistic considerations, that will be simply mc square minus m naught c square. But we understand that m is not absolute here, so m is m naught by under root of 1 minus v square by c square. And what we can do is we can think of using this m here, and the kinetic energy will be m naught by under root of 1 minus v square by c square minus m naught c square. Now, so here I have its own m naught c square. So this m naught c square can be common, and what will remain inside is 1 by under root of 1 minus v square by c square minus 1. That will be the case. But as we know, what we have is we have the minimum threshold. The minimum, sorry, this is V minimum. It is simply C by mu. Okay. So if we use the same formalism here, what we will have is we will have m naught c square times 1 by under root of 1 minus v, instead of v square, what I will have c square by mu naught square, and c square will cancel, so it will be 1 by mu square. That should be the case. So finally, what we will have is this kinetic energy. It will be equal to m naught c square times. So we can have LCM here. Then mu square and mu will square and root will cancel, and mu will go up, and we will have down under root of mu square minus 1 minus 1. So this equation is going to give us the threshold kinetic energy of the electrons, of the beta particles that are used in order to produce the Cherenkov radiations, and then detect these radiations using a Cherenkov counter. Now, what seems to be the point of contention here is to talk about the important properties of these counters. Now, what is important here is at the very first, I would like to say that these Cherenkov counters that we have, they are essentially directional in character. So you can have interference under certain circumstances along certain directions, and the Cherenkov radiations are emitted in forward cone of an angle. That angle is given by cos theta is equal to c by mu v, and the direction of the incoming particle can therefore be measured using this equation. Now, a charged particle above the threshold. So what we have is threshold velocity. Now, if there is a charged particle whose velocity is greater than that of threshold velocity, can only emit Cherenkov radiations. Can only emit Cherenkov radiation. So this is an important point to be noted here. So all the particles who have velocities less than that of this threshold velocity, they are not going to produce any kind of Cherenkov radiations in that particular material that has been chosen. So hence, what we need is there is a need of proper choice of the transparent material. There's a need of proper choice of transparent material. And Cherenkov counters can be made to respond to the particles in a given narrow range of velocities. So the choice of this transparent material is a must. And the particles of lower velocity than that of this threshold velocity, they will automatically be rejected by the counter. And as the angle theta that we have here, that we chose in our original problem when we discussed it, that we had the beta particles moving on in this direction, and we had a transparent medium. And as this angle theta that we have here, this theta is given by it's given by cos theta, and that cos theta is c by mu v. Therefore, the velocity of the incident particle can be calculated. We can calculate the velocity of the incident particle by simply knowing the refractive index of the transparent material that we have used in detection. And then another important thing is that particles of different masses can be distinguished. Particles of different masses can be distinguished because of the same kinetic energy. The velocity the velocity of the incident particles is inversely proportional to the square root of the mass number. And this is a known fact, that this velocity of the incident particle is inversely proportional to the square root of the mass of the particles. Now, particles of different charge can also be distinguished using these Cherenkov radiations. And in this case, I mean, the Cherenkov radiations, the velocity of the charged particle is more. That's the most important point. Within the medium, the velocity of the charged particles is more than that of velocity of light in that very material medium. Only then we can have Cherenkov radiation. So there has to have, if we are able to generate the conditions where the velocity of the charged particles that we are bombarding on the counter, if their velocity is more than that of the velocity of the light in the material medium, they are going to produce Cherenkov radiations.